Hello, grade 8 science. We're going to go into our last portion of chemistry. So this is our final lesson before summer. So we're just going to do a quick little recap. So what is matter? So matter is anything that has weight or mass and takes up space. So just a quick little reminder, matter can encompass all sorts of different solids, liquids, gases. Last week we talked about kinetic molecular theory. So the idea that all matter is made up of very, very small, tiny particles. And in between those particles, there are spaces. And the spaces are dependent on what type of state the matter is in. So remember when we discussed gases? Gases have big particles between the spaces. Or no, sorry, they have big spaces between the particles versus solids, the particles are more tightly packed together. The particles are always moving. If an object is very, very, very hot and is in the form of a gas, the particles are going to be moving a lot faster versus if they are cold, they're going to be moving in a much smaller amount. And what makes these particles move is energy. Often this energy comes in the form of kinetic energy, so that's the energy of motion, and it comes largely due to energy being transferred. So when something is heated, so for example, a ice cube that is heated in a saucepan over a stove, that's going to cause these particles to move because that heat energy is being transferred. So we talked a little bit about the movement of particles. When you add energy to matter, the kinetic energy or the energy of movement of the particles increase. So we talked about that transition from solid all the way to a gas. So when particles move faster, they bump into each other and there's more space that is created between them. So we discussed this last week. So everything that we know or everything that we've seen is made up of particles. We also call these particles, and what we're going to talk about a little bit today is we're going to expand this idea of what exactly a particle is we call these particles atoms. So everything is made up of particles. We could substitute that phrase with everything we know is made up of atoms. So if you look at this pencil is made out of graphite. We went in really, really, really close, we would notice that there are graphite atoms that make up the lead of this pencil. So what you can think of when you think of an atom is you can think of if I split open something and tried to break something open, if I kept going, what I would reach is I would reach an atom. So eventually something becomes indivisible, so not breakable. That's the idea of what an atom is it is the smallest form of matter that we can have. So matter is made up of atoms. If we kept breaking that matter up into pieces, smaller and smaller and smaller, eventually we wouldn't be able to break things up and we would have an atom. So how small is an atom? Really, 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 really small. So we're talking smaller than red blood cells. So if you remember when we talked about biology, we have over 500 million red blood cells in our own body. We're talking very, very small when we're talking about atoms. And I've got a little video that gives you exactly an idea of how big atoms are.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, it's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. And that's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, and now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
So, as we discussed in the video, an atom is made up of 3 main components. So electrons, which we'll talk about, they orbit the atom. Neutrons, which are in the nucleus of the atom, and protons, which are in the nucleus of the atom. So we're going to go over each of these different parts of the atom together. So remember, when we're talking about atoms, we're talking about those very, 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 very tiny particles that make up matter. So in a pencil lead, we're going to have billions and billions and billions and billions of atoms, just like we had all of those little small blueberries in the grapefruit. So there's lots of atoms that are composing matter. Okay. So again, definition of the atom, it's the smallest particle of an element that retains the properties of that element. So every different element is going to have a slightly different type of atom. So copper's atom is going to look a little bit different from silver's atom, from hydrogen's atom. And we'll talk a little bit about how you can tell what type of element it is by looking at the atom. So all matter is made up of all matter is made up of atoms, and atoms are made up of subatomic particles. So subatomic particles are these little guys that we're going to talk about individually. So inside the atom, the easiest part to kind of remember is we've got the nucleus. So the nucleus is the tiny region at the center of the atom. Remember the very, very, very tiny marble that was in the blueberry that was the size of a football stadium. So in the middle of the football stadium, you have a marble, very, very, very small. That is the nucleus. The nucleus contains almost 100% of the mass of the atom. So it's densely, densely packed. All other atoms contains protons and neutrons. So atoms contain both protons and neutrons, and they have different amounts of protons and neutrons depending on what element they are. And I'll show you how to look at the periodic table so you kind of can look and understand how you would know that. So numbers of protons determines the charge of the nucleus and the identity of the atom. So depending on how many protons are in the atom, I can figure out what element it is. So hydrogen only has 1 proton. Oxygen has 8 protons. So we can count the protons, and that's how we tell what type of element it is. Around the atom, so not in the nucleus, we have electrons. So electrons are small things that rotate around the nucleus. So the region that the electrons occupy is over 99.9% of the atom's volume. So the majority of the atom, so this one's quite blown up out of proportion. Remember, we're talking about the rest of the football stadium that is not occupied by the marble. So that's how big this portion of the atom is the electron energy shells. Electrons, which orbit the atom, occupy specific regions, or we call them energy levels that surround the nucleus. So they orbit the they orbit the nucleus, and they're in different levels based on the amount of energy. Electrons are spread out, kind of a little bit like a cloud. You'll see some models, we'll look at one where they're spread out in rings, but they kind of are a little bit more loosey-goosey than that. It's just easier to look at that type of diagram. So electrons are spread out like a cloud of negative charge that exist in the whole region at once. So this whole area is all negative charge. So we've got positive charge in the middle from our protons, negative charge on the outside from our electrons. So again, as I was mentioning, this is another kind of way of looking at the atom. So we're still thinking of this guy, just a little bit of a different diagram. We've got our nucleus in the center, and then we've got around the atom, we've got what I'm talking about when I'm talking about energy shells. So the amount of electrons is going to be the same as the amount of protons in the atom. So electrons can move different energy levels. So if energy is absorbed by the atom, so during a chemical reaction, for example, electrons can shift one energy level. If energy is released, they will go down an energy level. So they jump to higher energy levels by absorbing energy, so when they have energy added, and they go lower when energy is released. So if you follow me, inside the atom, we've got a very, 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 very small nucleus. It's the heaviest, most densest part of the atom. So most of the atom is really packed in that space. It contains protons and neutrons. Protons are positive. We're going to talk a little bit about them. And this affects the charge of the atom. So the atom can either be positively charged or negatively charged. And it also affects what type of element the atom is. Electrons are rotating around the nucleus. They occupy the majority of the space of the atom. So they're taking up the majority of the space. Not like this diagram. This is just big enough so we can look at it and see it. We're thinking about the marble with inside the football stadium. And most importantly, electrons can move. So how we tell electric charge. So electric charge comes in two types. So the electric charge of an atom can either be positive or negative. So protons equal a positive charge of 1+. Electrons equal a negative charge of 1-. Neutrons are neutral. That's how I like to remember that. So neutral, don't think negative, think neutral. So positive, negative, neutral. When we think of two ends of a magnet, we can think of how if I had two positive ends, what would they do? Stick together? No. What they would do is they would repel each other, right? They don't want to stick together. Versus if I had a positive end and a negative end, they would stick together. So positive, positive would repel, negative, negative would repel. Opposite charges attract one another. So if I have a positive and a negative, they're going to come together. So the overall charge of an atom is I typically would have a balance of protons and electrons. So if I have 7 protons, I'm going to have 7 electrons. So then I have a balanced atom. Overall charge of the atom is 0. So in an atom, we typically have the same number of protons as we do electrons. So number of protons equals number of electrons. So scientists discovered this, and what they did is they decided to classify all of the different elements based on the information that they could find from atoms. So for example, the hydrogen atom only has 1 proton and 1 electron. So they know that something is hydrogen. When they look at the atom, they can actually tell by looking at how many protons there are. If we look at something like oxygen, which is number 8 on the periodic table, there are 8 protons and 8 electrons if we have a balanced atom. So all of the different elements that exist around the world, so things like hydrogen, oxygen, fluorine, you'll remember if you know what fluoride is, which is in your toothpaste, neon gas, aluminum, silicone, all of the different elements that make up all of the things that we use in our life are classified on this periodic table. So there are many different elements that exist on Earth. So chemists decided that they wanted a way to organize and group all of these different elements. So what they did is this man in 1867, Dmitry Mendeleev, so this guy that's over here, he found patterns in the elements and organized them into a table. So he organized the elements based on their atomic number. So atomic number is the number of protons. So we've got atomic number right here is this number at the top. So that's how they're all organized. So it goes all the way from 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. And you may ask, why is there this giant gap in the periodic table? That is because the different elements are organized by what type of element they are. So we've got gases over here, we've got some metals over here, etc. Okay, so we've got all of it's kind of based on how it, what kind of thing it is. So he organized these elements based on their atomic numbers. That's the number of protons. And the elements are characterized by their atomic number. So this is become known as the periodic table, which you'll get more familiar with when you start using it in grade 9. So when we're looking at a section of the periodic table, so in the middle here, we've got a symbol. So that symbol represents the element's name. So Ti stands for titanium. So the name is titanium. The symbol is Ti, so that's right there. And then we've got the average atomic mass. So that's how heavy the atom is, which is down here. So atomic mass is going to be down here. We've got the atomic number. So the atomic number is always at the top, and that's also representing the number of protons. Typically, if we have a balanced atom, that's also going to represent the number of electrons. However, atoms aren't always balanced. So if I've got an oxygen atom that's got 8 protons, it doesn't always have 8 electrons if it's not balanced. So how we know an atom is not balanced is if up in this corner here, it has a charge. So in this case, we've got a +4 charge. That means that I am short 4 electrons. So it's 4 more protons. So typically the overall charge of an atom is 0. Relationship of number of protons and number of electrons that an atom has is typically an atom is neutral, so the number of protons equals the number of electrons. I'm just going to do a little practice, and then I'm going to give you guys a little task to look at. So the element here we're looking at here is potassium. So I'm going to look here. So this is potassium. That's the name of the element. The atomic number, remember I mentioned, was at the top. So the atomic number here is 19. That number is going to be the same as the number of protons and the number of electrons. So the number of protons is always going to be the same as the atomic number. Sometimes we're going to have a charge, so positive or negative, that's going to be related to the number of electrons. So here we've got potassium. The atomic number is at the top, so that's 19. Our average atomic mass is going to typically be at the bottom. My number of protons is going to be 19. And then my number of electrons is also going to be 19 because it's a balanced atom. This one is named boron. The symbol is B. The atomic number is always going to be at the top, so 5, which means that it also has 5 protons. This atom is balanced because it doesn't have a positive or a negative sign, which means that it's also going to be 5 and 5 electrons. Its atomic mass is going to be listed underneath, so at 10.8. So I've got 5 and I've got 5. One thing that's kind of tricky and gets confusing is the whole idea of elements is a different kind of idea. So the idea that aluminum is an element. One thing that confuses students sometimes is that they get confused between the idea of an atom and a molecule. So an atom is the smallest particle of an element. It can't be broken up any further. So if I have a tin can, if I break it up into very, 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 very tiny pieces, eventually I'm going to get to an atom. Okay, so that's an element. A molecule is a combination of 2 or more atoms bonded together. So for example, here I've got H2O. If you ever heard of H2O, we're talking about water. So here's my two H atoms. So those are my hydrogen atoms with their one proton and one electron. And they've been bonded together with this oxygen atom. So if I counted this, 1, 2, 3, 4, 5, 6, 7, 8. So that's oxygen. That's a molecule. So something like water isn't an element. It's a molecule. So it's a combination of two elements. And we're not going to get into that, but I want you to kind of understand the difference is an atom is an element. So we're talking about something that exists on this periodic table. Okay. So we're going to just quickly talk about what your last assignment is. So what you're going to do is you're going to play around with the PhET simulator. If you do not have access to a computer that has Flash and you cannot use the PhET simulator, please let me know and I will provide you with an alternative assignment. But I think that this one is really the best activity for you guys to do to really get a kind of handle on exactly how atoms work. So you're going to go to the website. You can just follow the link and you're going to use the tools to build any 3 different types of atoms and fill in the information about them below. So you will know that you have a different atom by the name. So the name is going to change. So I'll just show you. So you're going to change by altering the number of subatomic particles. So these are the 3 types of particles that we talked about. So protons, neutrons, and electrons. And that's going to create some different effects. So the first thing we're going to do is we're just going to kind of experiment. So I've got it all open. So what you're going to do when you get here to start is you're going to click on this. It's going to ask you for different things. We want to do the atom one. Okay. So what you're going to do is you're going to take some time and you're going to experiment with putting different amounts of protons and neutrons in your atom. I want you to open up these 2 sections. So what you can do if we first pop our protons in. So remember that the proton changes whatever element it is. So if I have 1 proton, I've always got hydrogen. Doesn't matter if I have a gazillion electrons or neutrons, I'm still going to have hydrogen. So what you're going to do is you're going to experiment with putting different elements in to your thing, and you're going to look at how it affects the net charge. So what happens when I add multiple electrons? What happens to the charge? What happens if I add more neutrons? And what you're going to do for each of the 3 elements you're going to do is you're going to write down the title of the element, so hydrogen, and you're going to write down the mass. So that's part 1. Next question. What subatomic particle, remember subatomic particle referring to protons, neutrons, or electrons, is the boss of the atom? So which one has the most control over what the atom is? Explain why. Then you're going to create a hydrogen atom. And then you're going to experiment with adding a neutron, adding an electron, and adding a proton. You're going to explain to me what happens to the overall charge, to the mass. Does the atomic number change? Does the type of atom change? We're talking about, actually, we won't do that part. I'll get rid of that. So you're going to record all of your changes when you add neutrons, electrons, and protons. Based on what you've observed, which 2 particles appear to determine the mass of the overall atom? So which ones control the mass? So you're going to watch the mass section on your screen. Based on what you've observed, summarize the relationship between how protons and neutrons, electrons affect the overall charge of the atom. So how is the charge changed by these different components? If you've been paying attention, you should have noticed that the term ion appeared from time to time. Experiment with the simulator to list the 2 ways you can create a positive ion and a negative ion. Write down your understanding here. Click on the symbol at the very bottom of the simulator window. Pick 3 new atoms to create. Display a sketch of the atom as well as how it would appear on the periodic table. You're going to try the game, which we saw when we started the app. What are the 2 fundamental particles that make up protons, electrons, and neutrons? We don't need to worry about that. We don't need to worry about gluons. And then how would you explain what matter in an atom is to an 8-year-old? Okay, so this is the task, your last task. Take some time to explore this. Remember to try out the game. And that is all. Good luck.